Hello, welcome back to the course on other signal processing for music applications. This week that we're talking about sound transformations, in the demonstration lectures we have been exemplifying the different models that we have been talking about during the course and some transformations that can be done using those models. For example, on the first class we talked about the short time Fourier transform as it can be used for morphing. On the second one, we talked about time scaling using the sinusoidal model. And then on the last one, we talked about how to do pitch changes using the harmonic plus stochastic model. Now I want to go back to the idea of morphing, but using a different model. In this case, we're going to use the harmonic plus stochastic model. And we will be showing that with this model, the type of morphing that we can do is very different from the type of morphing that we're able to do with STFT. So in order to do the morphing, we first have to have a good analysis of each of the sounds that we want to morph. So let's start with the GUI, the SMS Tools model GUI, and let's go to the harmonic plus stochastic. And so let's start with one of the sounds we're going to morph. We're going to morph the violin sound with soprano sound. So let's start with the violin sound. Okay, this is the sound. So we have to choose quite a few parameters. The Blackman window is a good choice for this stable note, and the side lobes are quite low, so that's good. We have to choose the window size, and that always requires some computing. So B3 is around 246 hertz. So in order to decide the window size, we just take the number of beans of the window, which is 6, times the sampling rate, 44,100, divided by the frequency of this note. Okay, so we need around 1,075 samples. So let's put it here, 1,075. The window, the FFT size has to be larger, so let's make it quite large, so we get a lot of zero padding, 4096 for example. Okay, magnitude threshold minus 100 is fine. Minimum duration of the sinusoids, yeah, it's a single note. We want to do interpolation with another sound, so the longer the better, so 0.5 would be good. In terms of the maximum number of harmonics, again, we want quite a few, as many as we can, so 100 is also okay. Now, in terms of the range of the fundamental frequency, we said that it was 246, the fundamental, so definitely this has to be below that. If we do from 200 to 300, that should be okay. And the F0 detection error, well, 7 should be fine. The deviation, yeah, 0.1 should be, it's quite a bit, and it's fine. And the stochastic approximation, yeah, let's not do too much of an approximation, so we get a good quality of the residual. So let's 0.8, the maximum would be 1, which would be the whole magnitude spectrum. 0.8 is okay. So let's compute it. Okay, this is good. Now let's listen to the sinusoids. Okay, this is fine, the stochastic. Okay, that's it's quite noisy, but it's soft, and it's okay. I think we can manage that. Okay, and here we can see this representation. We could try other parameters, but let's leave it like that. And now let's analyze the other sound. Let's analyze the soprano sound. Okay, and this is an E4. So now again, let's listen to that. And let's keep the Blackman. The window doesn't have to be that large, so let's choose the window size. It's 6 times 44,100, and an E4 is around 330 hertz, kind of. So it's 330.0. Okay, so doesn't need to be that large a window, so let's leave it as 801. And FFT size, well, let's leave it big, so that's good. Threshold minus 100. duration 0.5 is fine. Let's keep the number of harmonics. It has to be the same number of harmonics because we're going to be interpolating the two of them. So 100 is fine. And now, since the frequency was 330, let's now, the voice has a vibrato, so it will change quite a bit. So let's be safe and let's put from 250, for example, to 400. Okay, and now we can just leave the same parameters, the same error threshold for the F0 detection, the same deviation, and the stochastic factor of 0.8. So let's compute that. Okay, it's a little bit more difficult to analyze this sound because of the formants. There is some areas of the voice that there is not much, and but let's listen to the result. The sinusoids look good. The stochastic sounds okay, good, and of course the sum is fine. Okay, now we are ready to go and to do the actual morph between these two representations. So let's close these and let's go to the transformation directory and let's type Python transformations GUI. This is the interface for the transformations. So now we can go directly to the HPS morph option. And in fact, the sounds that we're going to morph are already the default ones, so we'll use those. But now let's change the parameters to the ones we decided to use. So we decided to use of the size of the window for violin 1075 and FFT size big one 4096, the threshold minus 100, the minimum duration of a trajectory we decided 0.5, and given that this frequency is around 246, we decided to use from 200 to 300, and now the error threshold we set 7, and here maybe we can be a little bit more open and just say 0.05. Okay, and for sound 2, the soprano, we're going to use the same window, Blackman. We're going to use a smaller window because it's a higher pitch, so it's 801 is fine, and we decided to use the same FFT size and similar values for the rest. So for the minimum, this is a higher frequency, so it's we need to, it's 300 something, so we need 250 to, there is no need 500, 400 should be enough, and this 7 and this okay, so we can now analyze. I wanted to change the number of harmonics. It has to be the same number of harmonics, and we set to have 100 harmonics, and the stochastic factor, we wanted to have a good stochastic component, so we set 0.8. Okay, let's try it again. Okay, so these are the two sounds. Clearly on the violin it found more harmonics than on the voice, so that means that we are only going to be able to interpolate the harmonics of the voice. So now what the transformation will do, it will be interpolating these two sets of values, and we have 3 ways to interpolate the set of values. We can interpolate the frequencies of the harmonics, we can interpolate the magnitudes of the harmonics, or we can interpolate the stochastic component. So let's, for example, let's just have the frequencies of sound 0 of the first sound. So let's put that at time 0 we'll have the sound, the first sound, which we'll refer as 0, and at n we also have the first sound. So basically the frequencies are of the violin, and the magnitudes, let's say, are of the voice. So we'll put that at time 0 we'll have 1, which are the magnitudes of the voice, and at 1 we'll also have that. And for the stochastic, well, we can just put 50 and 50, so we can just put at time 0 0.5, that means in between, and at times 1 we will put 0.5. Okay, let's see what happens. Okay, so this is a result, And the frequencies clearly look the spacing of the violin, but let's see the magnitudes, we don't see them here because we don't see the magnitudes of the lines, but let's listen to that. Yeah, so clearly it sounds what it is. It sounds a little bit the magnitudes of the voice, but at the pitch of the violin. Now let's go from one to another. So if we go from all the values of the violin to all the values of the voice, we can just do it by putting 0, 0, 1, 1, and again here 0, 0, 1, 1, and here 0, 0, 1, 1. Okay, and let's apply it. Okay, and here clearly we see that it's going from one sound, and here from the frequencies we see that there is this kind of glissandi, which is because the pitch of the voice is higher than the pitch of the violin. So let's listen that. Okay, so clearly we see this evolution. And of course, in these we have an envelope that we can specify any interpolation and in any time-varying fashion. So we can have quite sophisticated interpolation envelopes. Clearly, this is very different from the short time Fourier transform that we did. So if we, okay, let's finish this. And basically we have talked about a transformation, the morphing, using the harmonic plus stochastic model that's within the SMS tools, and clearly is a different type of morphing. It has different possibilities than the STFT. We can now interpolate basically every set of parameters and obtain any sound in between. So even though we are using the same term, morphing, the model has a big impact on the possibilities that the technique offers, and what we can do with this idea of interpolating between two sounds. So that was all. So hopefully between these demonstrations you have gotten an idea of the different possibilities that these different models offer for transformations. And of course there is many more possibilities, and some models we have not used them, and they also offer different transformation possibilities. So feel free to do it by yourself. So thank you very much for your attention, and I will see you in the next lecture. Bye bye.